Hi everyone. So now that you know how to find oxidation states of an element in a compound, we'll be able to define oxidation and reduction in terms of oxidation state. So whenever you have oxidation, there's going to be an increase in oxidation state, and whenever you have reduction, there's going to be a decrease in oxidation state, which means that you'll need to find the oxidation state of the species at the beginning of the reaction, so on the reactant side, and in the product side. So let's see the first example. So we're going to find the oxidation state of each species. So calcium, it's an element in an uncombined form, so oxidation state is 0. SN2 plus, so it has charge 2 plus, so oxidation state is plus 2. Then C8 plus has oxidation state plus 2 because it has charge 2 plus. SN, element uncombined form, has oxidation state 0. So as you can see here, so calcium is changing from oxidation state 0 to plus 2, which means that you have oxidation here. And SN is changing from 2 plus to plus 2 to 0. So here you have reduction. Second example. So again, we'll find oxidation state of each species. Hydrogen element, oxidation state 0. Oxygen element, oxidation state 0. Here in H2O, you'll need to find the oxidation state of the H and oxidation state of the oxygen. So normally, hydrogen has oxidation state plus 1 and oxygen has oxidation state minus 2. Okay, so as you can see here, hydrogen is being oxidized and the oxygen is being reduced. Let's take this example now. So again, we're going to find the oxidation state of each one. So let's see chlorine here. So chlorine element oxidation state 0. And if we find the oxidation state of chlorine in here, so this is NaCl, so that's going to be, so Na is Na plus, so Cl minus, so oxidation state minus 1. In NaClO3 here, so we're going to calculate it. So Na is going to be plus 1, Cl is unknown, oxygen is usually minus 2. So when you calculate it, you get the oxidation state of chlorine to be plus 5. So here, chlorine is plus 5. So in this equation, what is happening is that the chlorine is getting reduced and is getting oxidized at the same time. So it's the same species, the same element that is being oxidized and reduced simultaneously. And this is happening in the same reaction. And this is known as disproportionation. This is an important term, so you need to know this. So this reaction, this example, this is an example of disproportionation reaction. So it is also a redox reaction. Now we're going to see how we can use oxidation state in nomenclature. So sometimes you have compounds where the same element can have variable oxidation state. For example, here where you have iron with oxidation state plus 2, this used to be called ferrous oxide. And here we have iron with oxidation state plus 3. This used to be called ferric oxide. So there was a lot of names that you had to remember with the traditional nomenclature. So this has been changed to a more recognizable and unambiguous system. So this is why now we use the Roman numerals. So instead of having ferrous oxide or ferric oxide, now FeO, this is going to be written as iron 2 oxide. So the oxidation state is written as the oxidation number in brackets as Roman numerals. And here you will have iron-free oxide. So this is pretty simple here as well. So you'll have to know the oxidation state of the copper so that you can name it. Now here, manganese oxide, if you look at manganese and you find the oxidation state of manganese, so let's say it's X, so oxygen is -2, so X is going to be 4, plus 4. So here we're going to have manganese 4 oxide. Here, KMnO4, this is what we used to call potassium permanganate. So this is the traditional naming system, but now we call it potassium manganate 7. So the 7 indicates the oxidation state of the Mn. Then there is another compound of manganese, which is K2MnO4. This used to be called potassium manganate. But with the new nomenclature, this is now called potassium manganate 6. So you have to be careful with the nomenclature. Writing potassium manganate alone without any Roman numeral is not like the right way to write it. Or even potassium permanganate. We don't use that old nomenclature anymore. So now when you're writing the names of inorganic compounds, make sure that you mention the oxidation numbers of especially the transition metals, those that have the variable oxidation states. So be careful. So potassium, it's either potassium manganate 7 or potassium manganate 6. We do not use potassium permanganate anymore, or just potassium manganate. You need to include that oxidation number here. Now you have these two compounds here, and when you calculate the oxidation state of chromium in each of these two compounds, you find that the oxidation state of chromium in both is +6. Okay? But the only difference here is that in this compound, you have 2 chromium atoms. So this one is called potassium dichromate 6, and this one is called potassium chromate 6. However, this method is only applicable when you have metals that have more than one oxidation state. For example, if you have Na2O, sodium always has oxidation state +1. So it's actually not worthwhile for us to write sodium 1 oxide. So why would we even write that? Because we always know that sodium will have oxidation state +1. So just writing sodium oxide in this case is good. Now, for the sake of finding oxidation states as well as for naming, the formula and the names of these oxoanions are important for you to know. You should know the formula and you should know the charges of these anions.